topic. Sorry, I'm really sorry. We're running out of time. There is a session for the speakers' corner after our session.
We'll be happy to talk with you, Max, after the break.
So, our next topic is improving robustness of network management in zonal architecture. I'm delighted to introduce Hong Bengtsson. Hwai is a technical expert in vehicle communication at Volvo, Sweden. She earned her PhD in computer engineering from Chalmers University of Technology and prior to Volvo. Her current work focuses on Ethernet-based zonal architecture in vehicle network security and real-time network. Please welcome Hong Bengtsson.
Okay, good morning. My name is Hong Bengtsson. I'm from Volvo Cars. Maybe many of you already know me. But today I jump out from my comfort zone, not do presentation about Ethernet or architecture, but about something else. So bear with me if something are not correct or something are not perfect, that we can have a discussion after. And any comments are welcome. Before I start anything, I would like to thank Technica presentation yesterday. If you listened to Thomas and Vlad about network management and e-fuel system, he already mentioned all the challenge we have. Okay, it's when moving from domain architecture to zonal architecture or centralized architecture, it's no longer about mechanical on-off. It's a lot about the software, about the application, want to wake up something. At the same time, we have to keep the power efficient in the car. So how can we do this? Let's start with what we call the product availability. So Kirsten and many people have mentioned, the customer doesn't care what mechanism we use, what Ethernet or ASA, Moslink or GMS and whatever, they don't care. When into the car, they want to have a convenience, right? So that at the end, it's a convenience. That is we want to provide to our customer and want them to come back. And also to be able, especially at Volvo, is a safety. We have to pass through a lot of legal requirements. So in product availability, we have a lot of things about legislated availability. We have a customer experience, we call UX-related availability, when the vehicle work. Also, when in the something go failure or degradation, for example, in the crash mode, how quick you get out, how quick you send signal. On the e-call, on Volvo on-call, how fast you can do this, okay? So all of it put requirements on the network management or resource management. It include both power management and network management. Also, so if you look at this picture here, we divided by different zone. How close a customer, how close the driver go to the car. So if you can wake up like a different, it depends on the distance from the person approach the car, how close they are. So the closer, the more difficult to do the wake up. If you send the wake up signal from 7 meters or 10 meters, it's easy. You have a time to do something, right? But the more you come closer, you open the car, the faster you have to do it, like you do with the key or the NFC card. So here is an example of how can we work with this and what requirements, what latency, what timing requirements we have in our system. So we have something called phone as a key. It's quite become popular nowadays, I guess. So the first zone that is quite easy to achieve is as you come to the car like a 10 meter, wake up the car without any obstacle. So that one is easily done because the time for the request signal go to the car and then you wake up. And then the second zone is like about 7 meters. And the third one, more difficult if you come closer, about 5 meters, and some obstacle in between. And then the last one is very close to the car, but then also, if you have a phone in your pocket and you're moving close to the car, you don't want the car keep wake up, then it can draw the power, right? So which function to protect these kind of things? So here's a timing requirement to be able for the car to pass. Before we say that, okay, this car is the pass on the process. So the time for open door, you see on the number here. And the worst case is that you come closer to the car, then you have to open door in less than 1 second. And the less is the better. So we do all of these tests before we say that it's okay. So how do we do it? So today I give you a different view from what Thomas presented this day is concrete in how we implement these kind of things. So we come from we make customer user experience as the first, okay? Product availability requirements. From those, we break down to different use cases. And then for each use cases, we do a system design. Oh. Yeah, and then we have a number of details. We have a state machine to control each state, which vehicle mode, which vehicle state. And we have also sequence diagram that allow you to test, is it correct? And also measure on the timing. And then next time is that we have this requirement implementation. And then from that, we have a requirement to each node in the system. What do they need to fulfill? For example, selective wake up and so on. And at the end, it's a very, very important experience is that you need to do the test at all levels. So at the component level, at the domain level, and at the system level. And then if you do all of this, you will have a stable and robust wake-up shutdown system. So what is the challenge in the zonal architecture and how we do it? So you see there's this thing. So what Thomas didn't mention yesterday, or some of us asked him, okay, so what is the condition, wake-up condition? He's more about how to manage this using e-fuel system. But what my talk focus is about, okay, how do you manage? Do you know how many wake-up conditions you have in the cars? Okay, in what condition? So there's quite a lot, more than what you think. So that's very important to see, okay, when that's what we call the policies. It's like the police. Okay, you asked, can I wake up this? Can I wake up that part? If everyone asking at the same time, especially you share the resort, some app are using some ECU and the other app want to shut down. How can you do that? How can you monitoring all of this? So that's one we call this very important, this little box here. Because usually when you do domain architecture, or you win the car like a bottom up, then you do on the PNC and on the mechanism. So therefore, we are clearly differentiating between the wake-up shutdown policy and mechanism. And if you have a background in the computer system, you know that decouple between policy and mechanism is a key. You never, ever mix those two. And the reason is that whenever you change an ECU, you only need to test this part. You shouldn't change the policy. The policy should keep the same. Okay, so you can move a software or you can move a hardware, and by this way you can decouple between the mechanism and the policy. You decouple between the hardware and the software and system in the system. So that by having this approach in mind, so what we do is that, okay, we do this policy, who should take care of all of this resource manager in the system. So we do it centralized in something we call the vehicle brain, or should each of the zone have its own? So let's have a look. So you know this picture quite well, right? I have presented a number of times at AEC. So here in this picture, so here is the connectivity unit. Here you have all the ultra-wideband and wireless and so on. We have UXC who do the infotainment on the user experience, audio, video, and a lot of, especially important because they have a user experience when you see things. And then we have here, we call the vehicle computation unit, which is the vehicle brain. So in our centralized, full centralized architecture, here we have a vehicle control. Vehicle dynamic control is implemented in the VCU. And then we have a two zone controller, left and right. Here we have a vehicle motion, or on connector on the rim node, which is on other ECU. Here I have mainly on the CAN and lean, they are connected to zone controller. Okay, so when we do this architecture, when we move from domain architecture to this architecture, the TC10 is not ready yet. How can we do that? How can we wake up the core system when it's poorly Ethernet? So what we did is that we add extra CAN. This CAN only used for wake up the system. And then later on, actually it's a good thing because in the low power mode, we don't want this guy turn on because usually it's a very power consumption. Can we only make the system work in certain scenario with only zone controller? And this can also do. Okay, so that is the benefit of this. Now, I just want to mention about the wake-up mechanism in this slide. So for all the CAN, lean, and AutoSAR node, we still use the classic NM frame wake-up mechanism, and it works well. I already mentioned low power mode. For camera, LiDAR, display, we have an on-off switch. And for Ethernet, we want to introduce TC10, but the more work needs to be done. Is TC10 robust enough? And a lot of tests have been done with this. And I think that is to be nice to have a common wake-up mechanism for all the nodes in the system. So that is a wake-up mechanism. But as I said from the beginning, wake-up mechanism is not a major headache. Actually, it's simple. The policy is a headache. Okay, so there are two major approaches. One is a centralized approach. Here we only have one headquarter. So this headquarter decided, okay, any apps that want to wake up system will send a request. I will have a picture on the next one. Maybe we do this one. Take this picture instead, it's easier to understand. So this the resource manager will be implemented in the VCU. Any app that want to request a wake up an ECU, it will send a request as a service. So here we are fully service-oriented architecture. We use a service for wake up and shut down. And then when this resource manager receives a request, it will then forward this request to the corresponding device proxy. So each ECU here have a device proxy, or a group of ECU have a device proxy represent the device. The device will know the ID which one to wake up. Okay, so this is a fully event-based system. So let's give a flexibility. So here you look, I want to here. So if application A want to wake up the ECU, some ECU here, it will send the request service to the resource manager. Resource manager will get the ECU ID and check the ECU status and set the device proxy status and then forward this request to the ECU. And one of the reasons we do this is that we don't want to have any vehicle control in the zone controller, so that's why we did this implementation. But this one is flexible, right? But it's very difficult to test because so many use cases. This one have to take care of. Okay, then we think about how can we improve this. So then we do the distributed approach instead. So instead of using the PNC or virtual function cluster in AutoSAR, we make something simpler. Okay, by that each zone controller here inside here we have a number of resource manager. Usually we call hold 10 nodes. The nodes that have a number of application sharing resource, they will have their own resource manager. So each of this resource manager will have a status of the ECU that connect to it. And the key thing here is that those guys talk to each other periodically. Okay? So periodically they send a very simple message to send the status. So they have their own table of, okay, in my team, who is on, who is off. And then I send this message to my neighbors to own. And we're doing it by broadcast. So own resource manager will receive this message, so they always have up to date. And they also, it's similar to routing table in the network, right? So they can know who to fight. So that is obviously, we done some tests, and it improve the robustness because they always have a status updates and periodically, and we don't need to deal with the virtual function cluster, which is more complicated because it involves both the software component and so on. And we have many non-auto start node as well. So example of how it works. So in this picture, let's say now we have a 2-zone controller, but if we have introduced one more zone controller in the roof, we could do similar. So each up inside will request to its own resource manager, and this one will know where to find the other one. Here, and then they have a sync status about cluster status sync, and also we use a request response so that they know if the ECU is wake up or not. So in this case, we don't miss anything. Okay, so that is how we have improved, and then what I call here is improve the robustness of the resource manager approach. So when how can we make this one simple then? Then we say that we introduce the resource cluster concept. It's similar to PNC concept, but each resource cluster now only includes the physical ECU, and it is use case related. Okay, so we know in which use case, which ECU should be woken up. There, I give you just one example. When you do this, let's say software download, everyone on, for example, and we have a charging, vehicle is not driving, then we have only the nodes that are related to charging on, locking, unlock, for example, remote opening. So only ECU that involved in this scenario on. Okay, so that much more simple than you do in AutoSAR one, but don't get defended now. I'm not AutoSAR expert, but I just want to make something simple. So now, so this here how it look. It look. How about so if you do some research, you can have this fault tolerance state update in the dependent system. So that's very classic in the dependent system. You can find this one. So meaning that if one resource manager get lost, you still have the other one can do the work for it. So that is how we do the fault tolerance thing. So that's a key of making the system robust. So this example here, every time, for example, application A can request cluster 1, 2, and 5. So I put 1 here, 1, 2, and 5. And then application B requests 1, 3, and 4. And then I ask one more here. So all the time they up to date how many resource clusters are on. So that is this concept. We think it make it more fault tolerance and also more robust. Now, come back to the use case from the beginning approach. How can we do this? So we define the cluster called the approach or unlock cluster. Here we have something phone as a key, and then we send this NM frame because they are connected using CAN. So they are connected to one of the zone controller. Here is a resource manager 2 in the zone controller left. And then when this message arrives, you can do authentication. We have a security here. And after do authentication, they will forward to the resource manager 2. Resource manager 2 will then find, okay, I turn on all the ECUs that in the unlock cluster. So they broadcast this request to activate on the involved ECU in this use case. And then it works. So I haven't done real measurement yet. So here are some numbers and some observation. So for example, if we use TC10, for example, then you don't need to wake up the MCU. We can wake up two zone control in parallel. So if you have the vector in the Ethernet frame, you can say, okay, which node you can wake up at the same time. But that saves some time. But you also work on CAN, so it's basically with those requirements, we achieve those requirements. Again, I would like to show more than this today, but save something for the next year conference in Growth and Work. If you come, I'll show you more. So that's, with that, I end my presentation here. And again, any comments or questions are very welcome.
Thank you. Thank you, Hawaii, for this presentation. So now we open the floor for the questions. So please feel free to hold the microphone.
Florian Wagner, ETAS, thank you for this nice talk. I'm wondering about this decentralized approach. If you do not get problems with synchronizing the knowledge because you make decision on your local knowledge while at the same time somewhere else a change could have happened already that you don't know about.
We do synchronize, so that's why we have an extra signal to synchronize. Yeah, so we have a, if you see here, sorry. We have an extra signal to synchronize here, cluster status sync.
Yeah, but if I make the decision on the VCU first before I receive the sync message, so these corner cases.
Yeah, there is this corner case, exactly. So we need to see how often we send this sync message, yes.
Okay.
Yes, yeah, I know. It could happen, yes.
Any extra questions? So thank you. Thank you again, Hawaii.
Thank you.